last lecture that we had, what we were saying was to come up with a full set of equations that we call it as a two equation models that instead of pre-specifying mixing length, like what we do in algebraic models and one equation models, we just solve two additional partial differential equations, one for epsilon and one for k, which is this is the k equation, and the epsilon equation you will see it in shortly, and then you come up with the value for your new t or the Reynolds, then this is the turbulent viscosity, and from there you can calculate the Reynolds stresses. So, um, as we said, the solution is to write another differential equation for epsilon, and it will be a two equation model, and that is called the K epsilon model. The K epsilon model was first proposed by James and Launder back in 1972, and this is a two equation model. This is a model transport equation in this um, approach. They are solved for K and epsilon, as we said. The flow and geometry dependent length scale specification is not required anymore, so it's a complete model. It was the first complete turbulence model proposed, except for the need of a specification of some few constants. You don't need to specify anything related to the whole flow field, and everything comes out as a result of the solution. It is still an eddy viscosity model, meaning that you still need the length scale, you still need the time scale, you still need the velocity scale, which is square root of your turbulent kinetic energy, the same as the one equation model. So the steps that have to be followed are like this. You have to first solve model equation for K, which we saw it above. Then you have to solve model equation for epsilon. So you need to derive a model equation for epsilon since its exact equation is kind of impossible to solve. Then you can calculate your new T, your eddy viscosity, from this relation. So you have your K, you have your epsilon. What you need is to put another, let's say, constant, which is more or less equal to 0.09 there. And then uh, it is an empirical constant. It is obtained from experiments similar to those that CCD that you saw before in one equation model. Once you have nu T, then you go and calculate the Reynolds stress and insert it in the Rance equations and solve it. Unlike the one equation model, here we do not need length scale to be defined. There will be some other constants rather than C mu, and we will see them in short. These days, you guys are dealing with commercial codes, and these constants are already embedded in these codes as default. There are 5 constants in total. C mu is one of them. If your results do not match with the solution, you need to tune these constants. So you hope that you will match the DNS or experimental results. So the missing point here is actually epsilon information. We need a model for epsilon equation, but before going there, I would like to give the exact transport equation for epsilon, and I will not derive it. I will write already derived version, and before that, we know the actual theoretical definition of epsilon. So theoretical definition of epsilon is 2 times nu times dui prime dxj dui prime dxj bar. So this dui prime dxj, this thing, is the gradient of the instantaneous velocity fluctuation multiplied again by the instantaneous velocity fluctuation. But I and j can go through 1, 2, and 3, right? I and j. So it could be, for example, dui prime dx, du prime dx, dv prime dy. So you have to do all these multiplications and summations and then get ensembled averaged, because you see the bar sign in here, over n numbers of samples that you have in your DNS or your experimental results. Then this corresponds to the actual epsilon. This is very difficult to measure in experiments as well, because this means that first of all you should be able to use an experimental technique that allows you to determine the instantaneous fluctuation in space. PIV is the only solution because it does give you spatial distributions, so you need to have instantaneous fluctuation distributions in space of all velocity components in all directions. Then you have to take the gradients of those fluctuations and do the proper multiplication, summation, averaging, and then obtain the actual epsilon value. Of course, in a turbulent field, these gradients, the xj's, uh, are very hard to obtain because of the experimental grid resolution. Your camera has a specific pixels, megapixels. In a PIV experiment, you have a measurement grid. So you take data at every measurement grid. So that measurement grid should be fine enough to resolve the smallest length scales in the flow so that you can take these gradients and find the spatial distributions. So it is very tough to measure these things. The other option is to use DNS data. The problem is DNS data exists in a very limited Reynolds number range. So in order to be relevant to engineering applications, that data is useless. Up to some Reynolds number, you can obtain the dissipation rate value, and there are other ways to estimate, not to calculate the epsilon from experiments. Those are all, of course, needed to actually see what's the real dissipation, but the actual theoretical definition of epsilon is this thing that you see in here. It says how turbulent kinetic energy is lost to heat. So this equation is the definition, but the transport equation for epsilon is something else. If you can solve the transport equation, then it will give you the time and spatial evolution of epsilon. This equation, the transport equation of epsilon, can be derived from the original momentum equation and also K equation with appropriate procedure similar to what you've seen before for one equation models. So the exact transport equation for epsilon is something like this. It's a very long equation, but you have in the left hand side again you have uh, local derivative, convective derivative, and then on the right hand side what changes actually this distribution of epsilon in time and space. You have many terms in there. You have triple correlations, for example, as you can see in here, of fluctuating velocity gradients. The energy dissipation physically occurs at the smallest length scales, and we know that the amount of this dissipation, meaning that how much energy is going to be lost, is determined by the larger scales because it is because that is where it is generated. So this equation is the exact transport equation. It's not a model equation. If you can somehow solve this equation, which is impossible, you will get the exact epsilon values. So, first of all, since we do not aim instantaneous flow solution, we do not have any of the terms that you have in here. So, uh, these are all uh, instantaneous ones. The triple correlations, the divergence terms and stuff. Neither instantaneous velocity fluctuations nor their gradients, many of those terms in this right-hand side of this equation are not in closed form. And like the triple correlation and the correlation of pressure velocity fluctuation gradients. So the left-hand side, as you see, is in a closed form. In a regular RANS type simulation, this equation is not being solved actually. So the right hand side is entirely replaced by completely different equation which is entirely empirical. So I will write it in here. In here what you see is the exact equation, and this is the model equation, model transport equation. We know that epsilon is a scalar. Epsilon is energy, right? So the indices are all dummy indices. Actually, in the exact equation, they are repeating indices, and there shouldn't be left any free index in the equation. As it is seen, the right hand side of the exact equation, this very uh, karma karışık part, it is completely replaced by some model terms. You see, completely different. For example, the flux divergence term, you have the flux divergence term ddxj, it is replaced by this. So it is nu t over sigma epsilon times d, d epsilon dxj. And again, it is similar to that thing we just got for the K equation in Ti prime using the gradient diffusion hypothesis. So this equation is in fact entirely empirical because you don't need actually you need many constants in here. See, these are all C mu, C epsilon 1, C epsilon 2, sigma k, sigma epsilon. So these are those five constants that I was talking about, and you see a list of these in in here. So the values are the default values for the constants that these values were proposed by Launder and Sharma back in 1974 for the standard K epsilon model. And if you compare the exact and model equations for epsilon, you can see how significantly the transport of epsilon is simplified. You just compare these two together. So you can maybe guess now how much difficulty this model could have where there is a need for correct modeling of energy dissipation. And this will be very limited to model that. Actually, over the years, people have derived other versions of K epsilon, such as realizable K epsilon and other stuff. So the standard K epsilon is the K equation which I wrote it in here, model K equation, and the model epsilon equation, which is in here. And those constants that you see that is shown in the table, and these are uh, all embedded in all CFD codes that you use today. Those constants are derived based on some experimental data which were specific to one experimental case. So there is no guarantee that you can use those constants in some other turbulent flow cases. There are a few notes about K epsilon model, and I wrote them in here. It is the first and simplest complete turbulence model. It is acceptably accurate for simple flows. It can be quite inaccurate for complex flows. Inaccuracies that we encounter are mainly due to the eddy viscosity assumption and the epsilon equation, which heavily depends on empirical constants. These C epsilon 1, C epsilon 2, sigma k, and sigma epsilon. Many modifications have been proposed over the years, like realizable or RNG, which is renormalization group K epsilon. The K epsilon turbulence model, as defined here, it was the actually workhorse of the industry for many years, and still it is getting utilized for some applications. There are right now other versions we have in late 1980s. We will maybe we don't have time to talk about them right now, but a modified version of K epsilon, which is called K omega model, and in 1990s a modified version of K omega, which is called K omega SST, shear stress transport model. And all these things started to actually branch out eventually. After proposition of this model, people started to do experiments to see if the constants need to be modified or not. And for very fundamental turbulence flows like grid turbulence, simple shear flow, boundary layer, and etc., they saw some deficiencies of this model in some specific physical flows, and they did corrections to these constants. Therefore, if you choose this model in your commercial CFD code, these corrections are already implemented, and there is a list of default coefficients, and you can play with those to match your results. Of course, during the years, the standard K epsilon is developed, and now, as I said, we have RNG, realizable K epsilon, we have K omega, and different varieties of that. And right now, we don't have time to talk about all these models one by one, but this K epsilon was the starting point of two equation models uh, that you see in your CFD codes.